University, and then Idris Ekwei from Lancaster. And first of all, Guy is going to speak to us on modelling and forecasting of network time series.
Okay, thank you. Is this microphone working? Because I can't tell. It's okay. All right, thank you. Thanks very much, Stan, and the program committee for inviting me to come here today. I was at the last one a couple of years ago, and it's very nice to see so many familiar faces. So you can see that the title of my talk, and as Chris correctly points out, this is part of the LETS project, which is funded by EPSRC and the RC UK Energy program. This is, I guess, one of 3 or 4 ongoing projects. Idris is going to be talking about another aspect in a little while. Another part of what we're doing is using locally stationary time series models to do forecasting. I'm not going to be talking about that today, although we will be talking about that at the WIP4 conference in June in Paris, which Xavier is organising. So you can go and spend a few days in Paris if you want to find out about that, or lots of other interesting things. So what I'm going to be talking about today is how you might look at modelling and forecasting of time series on networks. And so this is kind of a little bit of a departure for me, and it's comes out of some stuff that I did a few years ago on regression on networks, and now we're starting to look at how you might use the techniques for modeling and forecasting network time series. Okay. Now the other thing before I start is I should emphasize that I know fully well that the kind of single limited statistical method that I'm going to be talking about today, okay, is certainly not going to be the be-all and end-all of forecasting for whatever it is you want to forecast. Okay, epidemics or wind speeds. I mean, I've seen lots of fantastic talks by wind specialists, and it's absolutely amazing the number of things that people do to get, you know, really accurate and forecasting. So this idea is really just an idea at this stage. It's a very early idea. And in the end, it'll be designed to be used as a component in a much bigger, more rational, more sensible forecasting and modeling framework. So let's give you a little overview of what I'm going to be talking about. Here I'm going to be looking at time series that are defined on a network. The network could actually be real. There could be a real network there. It doesn't have to be energy. It could come from a number of different areas, or it can be constructed. Okay, you may have some idea of what kind of network would help you distribute information in the system, which would help you do modeling and forecasting. Quite often, if you've got a real network, then you may well get better results, but actually some interesting things come out of the cases where you construct the network. The aim is to do modeling of these systems, and I guess one of the key things I've been doing is, does this kind of methodology help you do forecasting? Is there actually something here? And the one thing I really like about forecasting is that it's brutal, okay? Because you can really tell whether you're going to be doing a good job or not. Whereas with regression, you can do simulation studies, and well, it may work, it may not. So forecasting is a nice area to work in. And essentially, the talk is really about a kind of trick. And the trick is, if you've got some complex time series on a network, is there a way in which you can dimension reduce this into a simpler system that you can use modeling techniques on to help you do forecasting? So it's a trick to try and transform the problem from one domain to another domain, do your forecasting in the other domain, and then transform back. Now, of course, this is a very well-trodden path. I mean, things like principal components analysis is a good example of something that you might do with a multivariate time series, for example, and there's many, many other ways of doing this. I'm going to be using an epidemiological data set as my main example, but I will say a few words about some wind data a little bit later on. And actually, one of the interesting things was the comment we had earlier about the release of data. I would actually welcome anyone who'd like to come and talk to me later and say, hey, I've got this great network data on the network and might be interested in using these techniques. Getting data in the medical community is a little bit easier for some reason. I'm not I don't think we need to go into that right now. But hopefully through showing you this example, you can see what it's doing, and then if you've got other data sets that might be useful or interesting, then it might apply to those as well. So the data set I'm going to be looking at are weekly cases of mumps at the county level in the UK for 2005. So there are actually 52 observations in this time series, so one observation for every week of the year, and there are 47 counties. Counties of England and Wales, for the purposes of this exercise, is just one county. The data was supplied by Douglas and Daniela from the Health Protection Agency, and the questions are the usual questions. What can we say about this data? What models can we fit? Can we forecast, in particular, early 2006? And mumps, of course, in this country is actually quite interesting, because it's about now that mumps is really starting to take off in some areas because of the lack of uptake of the MMR immunization a few years ago. Of course, it's measles that's really in the news at the moment, but mumps has also experienced an increase. Let's just give you a little picture of what some of the data looks like. And on the left-hand side, you've got the situation at week 1. Here are all the counties of England, and Wales is one county at week 1. And then at week 52, so you can see at the beginning of the year, Wales and Devon have quite high incidences of mumps. This scale is number of cases per county, ranging from 0 to 100. And then by the end of the year, Wales is still high, Devon's gone down, and there's a bit more going on in the east of England there. But notice the scale has dropped from 100 to 25. So maybe overall the cases have gone down. Where is the network? Okay, it's not maybe immediately obvious where the network is here, and this is an example of where we've done network construction, basically get a neighborhood structure between the different counties. But of course there are many different possibilities that you might want to use. For epidemics, you want to link it to somehow like people movement, transport corridors, linked by weather patterns for some kinds of epidemics. Here we're going to do something very simple and very elementary, which might not be correct, but the question is it going to help? We're going to link by geography. And in fact, just for this toy example, we're going to link the counties using a minimal spanning tree. Okay? And of course, you would almost certainly do better if you have a better network which really reflects what's going on in the system. So here's the network that we came up with using the minimal spanning tree, just linking the county towns. Wales, there was a town in the middle of Wales somewhere that was used for this. Well, what's the data like? So far I've shown you the network, the counties, I've shown you a picture of what the cases looks like. Well, as you won't be surprised, there's a very complex correlation and trend structure over time. Because we've got 47 counties, there is a lot of covariances, obviously higher order moments, there'd be a lot more information there. The covariance structure seems particularly full, okay, as you might see in a multivariate time series set. And there's a lot of dependence here. Let's show you some plots. So here I've got 2 time series of the number of cases, one in the county of Durham and one in the county of Tyne and Wear. Durham is the solid one. And you can see that there is some correlation there. Here's 2 other counties, Somerset and Avon. Okay, so these are both neighbouring counties. And in fact, if you assume that the series is a stationary series and you did a cross correlation between all of the counties, then you can see that actually there's quite a lot of these correlations here between 0.4 and 0.8 all over the place. There are 2 counties that seem to do the opposite to everywhere else, and they are Shropshire and Essex. For some reason. Oh, yeah. No, not getting into television here. But my point of showing this slide is that essentially there's a lot of correlation in this system. So one of the things that we thought might be quite interesting was we want to try and simplify this data set to get it to its essence, whatever that is. And we know that probably the 47 dimensions is too high. Okay. Not a lot of point in modeling maybe all these 47 time series individually or kind of collectively, because the actual real dimensionality of what's going on is possibly smaller. many high cross correlations between series, a lot of redundancy in the system. Can we dimension reduce it sensibly? So what are we going to do? So we've got these p time series, each of length t. There's a network structure linking the nodes. We're going to transform it to another set of p time series of length t, and as much as possible, have much less cross correlation. That's the main goal here. And actually, as a result, what tends to happen with this is the series will also have much less internal autocorrelation. And also, we have a trend component, but the trend component's going to be confined to a small number of trend series. Okay, so it's a sense we're doing a decomposition. How are we going to do that and get a simple series? Well, what I wanted to show you first of all is a picture of the cross correlations between, say, Durham and Tyne and Weir. So you can see they're pretty high, and that's almost certainly a mix of trend features, but also genuine cross correlations. And that's Avon on Somerset, so a little bit less there on the forward lag, but more on the back. Okay, and what's going to be interesting, these are the cross correlations and the correlations, autocorrelations before I do what I'm going to do, and what will be interesting to see what they look like after I've done what I'm going to do. So what am I going to do? I'm going to use a new method called net tree, which is a kind of lifting transform. And net tree is an example of lifting one coefficient at a time. And net tree is actually, you can think of it as a wavelet transform on a graph. Lifting is a generalization of wavelets to a variety of different spaces. One thing, so why are we using this? Why are we doing this? Well, one of the things that the standard wavelets are well known for is that they are powerful decorrelators of systems. Okay, and there's been a lot of work published on that. I can direct you to. That's just the reference for net tree. I'm going to explain what net tree does, and then I'm going to show you what happens to the time series. So we're going to call our nodes I going from 1 up to 47 in our example, and the value of the time series at node I is going to be Ci. And what we're going to do is somewhere in the network, we're going to operate our lifting transform, which is a sequence of steps, and this is what one step is. We're going to identify a network node I, and I'll tell you how we do that a little bit later. And we're going to choose somewhere in the network and say, this node here, I, we're going to turn this from the value that's there into a wavelet coefficient. Okay. So let me tell you what I do, and then we can interpret it a little bit later. So I've chosen my network node I, and I identify the neighbors of the node I. I'm going to call that Ji. And I'm going to compute or use the internode distances between I and the nodes of its neighbors. I'm going to compute node weights Aij, which are essentially 1 over the distance between node I and node J, and there's going to be a constant involved there, and the constant's chosen so that the sum of the node weights is equal to 1. Okay, so I've got the node that I've chosen, that I'll tell you how in a minute. I've got its neighbors, I've got the distances. I form node weights between the node and its neighbors. Why am I doing that? Well, essentially, I'm basically going to do something to this node, and I want nodes that are further away but still neighbors to have less influence on what's going on about what I'm going to do. And in fact, what am I going to do? I'm going to form a wavelet coefficient or a lifting coefficient, di, at that node, and it's basically going to be the value of the time series at that node at that time. And I'm going to subtract a linear combination of the values of the neighbors, and the linear combination I'm going to use are these inverse node distances. Okay? So essentially, I'm basically going to say, here's my node. I'm going to look at the neighbors. I'm going to form the difference between that node and the values of the neighbors. Okay? And neighbors that are close, they're going to have a higher influence, and neighbors that are further away are going to have less of an influence. And that turns basically a value of the time series into a wavelet coefficient. So here's a picture, a toy example. So I'm looking at 5 nodes, 1, 2, 3, 4, 5. The values of the time series are 2, 3, 7, 5, 4. The blue numbers here are the internode distances. And what I've decided to do is take this value here of the network, this 3, and I'm going to turn it into a wavelet coefficient. Okay, so that's the nodes, they're the values. That's what we want to do. They are the internode distances. 1 over the internode distances are those fractions there. carefully chosen those numbers so that they add up to 1 already, so I don't need to work out what the C is. It took me ages to do this. And so in this case, the Aij, that's equal to these in that case. So formalistic coefficient, that's the neighbor set, and that's just implementing the formula. And you can see what's going on here. So I've got the 3 is the value at the function at node 2, and then at its neighbors it's 2, 7, 5, 4, and that's the particular linear combination I'm going to use, and the value I get is minus 5 over 3. So the value of the function goes from 3 to minus 5 over 3. Now that becomes a wavelet coefficient. I can take it out of the system, and if I do that, I have to break these links here, okay, because it's no longer in the network, and I have to relink these 4 nodes here to get back to a connected network. And the other thing I have to do, I'm not going to go into much detail, is there was a kind of power associated with that function value, that time series value, and I have to redistribute that to its neighbors so that the overall power in the system stays constant at each step. But don't worry too much about this. So remove the coefficient, relink the graph. But the key point is, if you've got a function value, and essentially what you're doing is you're saying, what's the local variation in this little area? Yeah? If all the function values are roughly the same, you should get a very, very small coefficient. So overall in the network, what you're doing is where there are smooth parts in the network, you're getting a lot of compression down to very, very small coefficients. If there are discontinuities between neighbors, you're going to get large coefficients. Okay. So lifting will give you good compression. So here we are, we've taken the wavelet coefficient out, and we've redistributed the power, so these values have changed slightly, and that's one step of the lifting transform. We now go and find another node to turn into a wavelet coefficient. So the whole algorithm, you start with function values at the P nodes. How am I going to pick nodes? Well, I'm going to pick nodes with the smallest area, and there are various ways that we can define that on a network. I don't want to go into that now. Form a lifting coefficient at node I, and then just keep doing that. Find the next point with the smallest area, pick it out, turn it into a wavelet coefficient. And we keep on doing that until we end up with basically, say, in this case, NC, 2 coefficients that we don't transform. Okay, so here's week 1, all the values of the months on the network. And then if I form the wavelet coefficients for the whole system, then what would be interesting is if you focus on, say, these values here, so the 21, 15, and the 17. So there's a neighborhood structure there, probably the 7 and 12 are involved as well. And that 15, probably the 21 and 17 will actually turn into, well, that one hasn't, but these two have turned into smaller numbers. Okay? The red, well, they're basically what's left over at the end, the 2 things that I never transformed. And they're a bit like the overall mean left in the system. They're the trend values. And I'm going to be doing this, the same thing for the network at every time step. Okay? Now, for that, we assume that the network doesn't change, although it's an interesting problem. Could you do it with the network changing as well? But for this, we assume that the network stays fixed. So if you like, probably this 26.7 is kind of an overall mean for what's going on over here, and these are all the differences, the lift wavelet coefficients, and 11.4 is the northern mean, if you like. Now, one of the remarkable things about this transform is we're actually doing a dimension reduction at each time point. Okay? But let's now just pick on one of the network nodes, so for example, Durham and Tyne Weir again, and look at these wavelet coefficients through time. Okay? And if you do that and look at the cross correlations, they've basically disappeared, gone. Massive decorrelation. And actually, the autocorrelations, they've also turned into white noise, essentially. Okay? What about if I look at, say, Avon and Somerset? Well, again, here, for example, gone. Here, nearly gone. There's something there. And the correlations themselves have reduced somewhat. So as expected, kind of, there's been a massive decorrelation because of this wavelet transform, because of this lifting transform. What was a bit unexpected was this is conferred to the time direction as well as spatially as well. But it's very, very interesting. So there's a massive decorrelation. We end up with P minus NC wavelet coefficient series and NC scaling function coefficients. And generally, how are we going to model this? Well, if G is the graph, the network, we're going to let S of G be the set of scaling function, the mean time series, which in this case we're going to be 2. And then with all the wavelet coefficient time series, of which there'll be 45 here, we're going to divide it into 2 sets. One set, Z of G, is going to be the set of nodes whose associated series are white noise. And I think it's plausible from the picture that you saw there's going to be some of those. And Q is going to be the set of nodes whose series are not white noise, but they will have been decorrelated, and so there'll be less there. Less correlation there. And typically we've modeled Q by low-order armor processes. So for the mumps data, what comes out as the scaling coefficients? Well, actually, North Yorkshire and Wiltshire. They're the nodes associated with that. And what's interesting, if you look at the remaining 45 time series, 28 are deemed to be white noise. Yeah, that's pretty interesting statistic. 17 are low-order armor. So in other words, over 60% of what you have left get turned into white noise because of this decorrelation. And we don't just look at it and say, yeah, that looks like white noise. We actually apply the significance test to get at least some kind of objectivity in there. So for forecasting, what's so good about this? Yeah, we've turned one set of time series into another set of time series. Well, one of the interesting things about white noise processes is that they're very easy to forecast. That's really useful. Low-order armor processes are also pretty easy to forecast. So much easier than the stuff in the original domain. The scaling series, we treat those as a kind of trend. We just extrapolate those, and that's easy to do, and in this case it's very few of them, usually 2 or 3 or something. You get to choose that. The other big thing, of course, is because you've got this decorrelation between nodes, you can treat the forecasting problem as a set of separate forecasting problems. Okay, you don't have to worry about the correlation because it's essentially now all gone. So that's what that says. Okay, so I don't have a huge amount of time, but I did want to show you the results of a forecasting exercise for the epidemiology data set. On the left-hand side, a pretty standard, basic, simple forecasting method, and the same thing, but using lifting. So high forecast errors are the yellow colors, basically 0 errors are red. And I think you can see on the left-hand side there's a lot more error compared to the right-hand side. And typically, for this particular data set, we're looking at like between 5 and 15% improved performance. I am interested in looking at energy data sets, and historically I've done a lot of work with wind speed analysis, but on the kind of pure statistical side. I did find some data, but it took me a long time to get it. This was Midas data, so wind speed data from BADC, originally from the Met Office. And here we've got 721 hourly records. I just chose that for some reason at 102 weather stations. And again, I'm not going to show you any forecasting results, but I just show you this one plot. This is a picture that I'm sure many of you have done before. So it's a cross correlation here between 2 Met Office stations. So a lot of cross correlation. Obviously, a lot of things are in there, trend and seasonality and all kinds of other things, and autocorrelations here. And after you've applied the lifting, well, it hasn't got rid of the cross correlations, but actually they're a lot smaller than they were before. Hasn't done such a good job on the autocorrelation this time, but probably it's still actually it's comparable to before, but on this one it's decreased it again. So I look forward to working a lot more with this time series and getting more out of it. There's a lot to investigate this. I said this was very early day research in this area, certainly for us. I showed you just one formula on how to get the wavelet coefficients, this if you like, linear difference. There are different ways in which you can choose neighbors. What is the area of a node on a graph? I mean, there are various ways in which you could think about what that might be. How do you redistribute the weights? These are all questions on the lifting. How to relink the network. There are various ways in which you can do that. We have an equivalent transform for doing lifting for networks that are themselves embedded in Euclidean space, so the nodes actually have coordinates. The one I've shown here, there are no coordinates for the nodes. And we also have another version of lifting for points in Euclidean space. So there's no tree there at all. There's no graph there. It's just points in space. And that's called lift for. It would certainly be nice to hear of more energy network time series problems, not just wind, but anywhere else. And we're talking to some people about bits and pieces. On the statistical side, what models are useful in the transform domain? I've just shown you stationary time series models. One of the ambitions that we have is to think about using locally stationary forecasting, if that's what the data demand. How do we do optimal compression? That's related to the wavelet coefficient computation, and non-stationary and stationary forecasting. So that's with network time series. I think generally speaking, the analysis and forecasting of network time series is a very challenging and very interesting problem. And this network lifting is at least an exciting new method for doing dimension reduction. But don't get too excited. It's just a transform method. It's just yet another transform method, but one that's guided by the network structure. But what's quite interesting is that with the data that we've got here is that the transformers made things a lot simpler in those problems, and forecasting of the reduced series has been much easier, sometimes more accurate. You can read that. And then that's it. Yeah, thank you very much.
Yeah, I enjoyed that talk very much. I think we may have access shortly to some data from electricity substations, which are all connected on some sort of network and things like that. And when we've got that and we've got suitable permission, we'll send you some.
Okay.
Because certainly it is shareable. And while we're not interested per se in forecasting that at the moment, we're more interested in classifying it. Actually, it'd be very interested to see how you got on, and if you did get on, then there might be, some follow-on consequence for it.
Actually, one of the interesting things, I guess, is that it's not often the case that companies don't want to share things with you, and there's NDAs that can be signed and all this kind of stuff, but it's not quite in the right format in the database, or they didn't remember to record this bit or that bit, and it's going to be a hassle to get it. You know what I mean?
So this will be in a nice format.
Oh, good.
But we just have to get a little bit of permission. But I'm pretty sure we would be able to share it to do an experiment, and it'd be great to get you involved.
Yeah, good.
Yes, your method looks very interesting. As I understand it, the transform ought to remove the autocorrelations spatially, and it also appears to remove them temporally.
Mm.
Have you got any sort of theoretical underpinning for why it does it temporally?
I think one of the strong reasons is because the trend is being partitioned into two series, and you can kind of see why that, even if you do that spatially, why it's happening through time. So I think that takes out a lot of the autocorrelation. And obviously, if you have a time series with trend, one of the first things you're told is to take the trend out and then model what's left. And whenever you see an autocorrelation that decays really slowly, you can be pretty sure it's a trend or a seasonality that's done that. So I think a lot of that's caused by that removal.
Do you think there might be networks that have, because of their sort of internal structure, a tendency not to do that though?
Yeah, possibly. I haven't thought about that, but
One more question.
Do you have ideas about how to connect two different grids? I think for electricity, you can have a grid for the substation, for the network grid, and one grid for the meteorological covariates. And maybe you want to do migration from one grid to another. You have.
yeah, no, I haven't thought about that, but that's an interesting. Okay.
Okay, so should we thank Guy again?